So because square root 2 is equal to p prime over q prime. So if we square both sides, they should be the same. Okay, so we will have what? We will have square root, so let me copy it. Square root 2 is equal to p prime over q prime. So that this will give me 2 is equal to p prime square over q prime square. Is that okay? So what does it mean? So it implies that 2 times this q prime square is equal to this p prime square. Is that okay? This is even. This is even. 2 times a number is an even. A number square is even. So it must be an even number for p. Is that okay? This is proved by contraposition again. Because if p prime is odd, then p prime square is odd. So in that case, this is not okay. So in that case, p prime has to be even. Is that okay? So far, if you are okay with this, could you please raise your hand? Okay. So now our strategy is further, okay, to show that, okay, so if p prime is even, then we can write down p prime is equal to 2k for some integer k. Okay? Then what do we have? If p prime is equal to 2k for some integer k, then 2 times q prime square is equal to 2k square. And then this is equal to 4 times k square. Is that okay? So we will have q prime square is equal to 2k square. Okay? Is that okay? And then this is even. 2 times k squared is even. So we use the same logic again. Then we know what? We know that q prime has to be even. Is that okay? Okay, q prime is even. It is equal to 2l for some integer l. And what do we have? And now, suddenly, I'm announcing that we get a contradiction. I will let you to discover where is the contradiction. So there is a contradiction. Where is it? Suddenly, I have a contradiction. Where is it? Pardon? Yes, very good. The contradiction occurs. Look at this. Q prime is an even number. P prime is an even number, right? These two, okay, these two is still okay. It doesn't say anything. But it's but if p prime is even, q prime is even, then what does it mean? It means that p prime and q prime, they will have common factor. So from this sentence, let me call it A. From this sentence B, A and B will give me a sentence C. P prime, q prime, they will have common factor because both of them are even numbers. So the common factor, there is at least a common factor of 2. Is that okay? Now this is the sentence C. Sentence C is still there's still no problem. But together with this sentence D, then there is a problem. C says P prime, Q prime, no common factor. D says the choice of P prime, Q prime is the way that they don't have any common factor. One says they have common factor, one says they don't have common factor. So these two are together will give us a contradiction, always false. Is that okay? Good. So you understand the proof. Okay. Now, there is one key point here. This is like setting a trap. This is like setting a trap. so that later we can get a contradiction more easily. We start with something that is not true, nonsense. If we start with something that is not true, then there must be something that you can think of that we will. So if something is wrong, then there must be some weakness of it, so that it allows us to prove that it is wrong. So here, this is the trap that we are setting up, so that later when we fall into that trap, suddenly here we get some common factor, and then we say that there is no common factor, so these two will immediately give us a contradiction. Now, this is not the only way that we can set a trap like this. So if you are okay with this, we can do a slightly different proof by using a slightly different trap. Is that okay? So I'm going to remove this, and then we get a different way. So I'm going to use a different trap. Okay, so let me copy something down this. He's this. Here's the smallest inch. Okay, so I'm going to set another trap. So this is the trap that I'm setting. So we still have the same here. We assume that square root 2 is rational, so that immediately we say square root 2 is equal to p over q for some integers p and q. Now we know that square root 2 is a positive thing. So we may now assume, okay, if there are many choices for this p and q, we choose p and q both to be greater than 0. Is that okay? So at least I can choose q to be greater than 0. And then if q is greater than 0, then I can choose p to be greater than 0. Is that okay? So if you give me some p and q, and some of them are negative, then I multiply negative to the top and the bottom, then both of them becomes positive. Is that okay? Now furthermore, if there are different choice, so there could be different choice of p and q that we can choose to be equal to square root 2. And if there are more than one choice, then I will always pick the q to be the smallest one. Okay, so I'm picking q to be the smallest integer, such that if square root 2 can be written down as something like x over q, then q is the smallest one. Is that okay? So no, we should. So smallest actually, it is like we are removing some common factor as well. So there cannot be any, actually here, this actually implies that there cannot be any common factor between p and q, actually. But I'm not saying common factor at all. I'm just saying that if there are more than one choice of p over q, I choose the q to be the smallest one. Is that okay? So I'm using this sentence, this keyword, without loss of generality. So we are making an assumption, but this assumption does not make us anything wrong. It is because if this is true, then we can really find one that satisfies all the conditions, or further more conditions that we have. It is not like we are adding conditions to to, and then make the problem and make the solution gone. It is like we see that among all the solutions, among all the solutions or among all the choices for P and Q, there must be some choice that satisfies this case, so that we are going to pick those cases to use. So that's why we are saying that without loss of generality, we are not taking advantage of adding this and then make the solution gone. Okay, so this is something that we have. Now this is a trap that we are going to set. So here there is no P prime Q prime, but we are going to do things very similarly. So we still have now P over Q. Square root 2 is equal to P over Q, so that we will have 2 times Q square is equal to P square. Okay? And we will still have P is even. Okay? And then it is equal to 2k for some integer k. Now because P is even and it is equal to 2k for some integer k, then we will have what? We will have 2q square is equal to 4k square. The same as before, so that we will have q square is equal to 2k square. And then we still have q has to be even. And then it is equal to 2l for some l. Okay, so at this moment, we will have what? We will have square root 2 is equal to P over Q, and then it is equal to 2k over 2l. It is equal to k over l. Am I correct? And now we have a contradiction. Where is the contradiction? Where is the contradiction? What's wrong? Look at the trap. The trap says what? Square root 2 is equal to x over q for some. So this says q is the smallest integer that you can put as the denominator. It is equal to square root 2, right? And now what? And now you have L. What is L? L is only half of this Q. So L has to be smaller than Q, right? And then it has to be greater than 0. So L is some number smaller than Q. And then you can put it at the bottom so that it is equal to square root 2. So the contradiction occurs from the choice of this Q and L. So Q, we choose it to be the smallest integer. So here, this sentence says, so this sentence, let's call it A. Sentence says A is the smallest, A says Q is the smallest integer that you can put. And if you look at this sentence, let's look at this statement as a B. It says that Q is not the smallest integer. Because there is something that is even smaller than Q, you can put it as a denominator. So A says Q is the smallest. B says Q is not the smallest. So these two together will give us a contradiction. Is that okay? Now this is not easy. Okay, if you are not familiar with contradiction proofs, if this is your first time to look at the contradiction proofs, then this could be quite confusing. But hopefully the main idea is you start with something that is wrong, and then you should believe that at a certain steps you will find something strange. The strange thing is the one that you should look for. This will give you something always false. You start with something, and then this is the strange things that is happening. It is contradicting each other. One says, I'm okay. One says, I'm not okay. Then, are you okay or not okay? Then in that case, there is something wrong. Okay? So this is the contradiction proof. Okay. So the next one is a well-known result in number theory. It's not here, but it's easy. Okay, so theorem, it says, so first of all, everyone know what is a prime number, right? So a number is a prime if it is greater than 1. Okay, 1 is not counted as a prime. If it is greater than 1 and the only factors that this number have is 1 and itself. Okay, so prime numbers. Is that okay? So 2 is a prime, so prime. So what are prime numbers? 2 is a prime, 3 is a prime, 5, 7, 11, 13, 17, 19, 23, etc., etc. All the numbers in between, they are not primes. For instance, 12 is not a prime because it is divisible by 2. 18 is not a prime, it is divisible by 2. And then 15 is not a prime because it is divisible by 3 or 5. Is that okay? Good. The theorem here says there are infinite number of primes. So there are infinite number of primes. And then this one is best a very good example of proof by contradiction. So we prove by assuming that this is wrong. So this is wrong is what does it mean? If there are not infinitely many primes, then there are finite number of primes. Okay? So assume that, so you can make it more specific to tell us that you are using a contradiction proof. Assume, so we say that assume on the contrary. So this indicates that you are using a contradiction proof that there are finite primes. Okay. Now, if there are finite number of primes, then what does it mean? If there are finite number of primes, that means that we can list them out one by one. And then list them out, and it must stop at some point. So we can call these primes. Let's call these primes P1, P2, ... You can have a lot of them. I don't know how many, but let's say the last one is called the kth one, pk. Is that okay? Because there are finite number of primes, we can list them out, and then it must stop at some point. Okay? This is meant by finite. So it will run out. Then what does it imply? Okay. So now I'm going to set a trap. Let's set a trap. So let's consider a number. So let's consider this big number q. This big number q. So this q is constructed by multiplying all these primes together plus 1 and add 1 afterwards. We multiply everything together and then add 1. Okay? Now what? Q, if you look at Q is not divisible by P1. Because if you divide it by P1, then you have a remainder of 1. Q is not divisible by P2. Q is not divisible by P3. Q is not divisible by any of the primes. So here, Q is not. So because we construct Q in this way, Q is not divisible by any of the primes. If Q is not divisible by any of the primes, then what are the prime factors of Q? It doesn't have any prime factors from all the known primes. We have listed all the known primes. And there is no prime factor. So what does it mean? It means that Q has to be a prime, right? Is that okay? Q cannot be divisible by any of the known primes. Q has no prime factor from this part. No known prime factor. So it implies that Q has to be special. Q is a prime. Is that okay? Or if Q is not a prime, Q has some prime factor that is not listed in your list, then there is a contradiction. There is a contradiction. The contradiction says we have listed all primes here. And then from this one, we have not listed all the primes. All the primes are listed, all the primes are not listed. So we get a contradiction. So the contradiction comes, and it implies that the beginning assumption has to be wrong. Because if this is correct, then we should not have any contradiction. The only case that we get a contradiction is this is wrong. And if this is wrong, then the original theorem is correct. Is that okay? Now, this is a theorem about prime numbers. That is a theorem about square root 2. Both of these are included in the book by Euclid, the Euclid's book Elements. But somehow, this may be due to Euclid himself, and this one is known earlier, actually earlier than Euclid. So Euclid is a knowledgeable person. He gathers some known results and then collect them and also include that in his book. So this is even earlier than that one. Okay. So I hope you like it. So today, we have finished the proof by contradiction. So next week, there are some other proof techniques like proof by cases or how to prove equivalence. And once we talked about that, we will talk about induction. And then this will be the last topic that is included in your first exam. Okay? Okay, that's all. Thanks a lot.